Hi, everybody. Welcome to the, what is it? October 2022 edition of the Eastern Java User Group meeting. Thank you all for joining us. Thank you out there on the internet. If you're watching from YouTube and watching this as a recording, glad to have you here with us. My name is Jim Bethencourt. I lead the Eastern Java User Group. And tonight we have Garrett Grunwald and sorry. And he's going to show us all about a new technology called CRaC, Coordinator Restore Checkpoint on, and it runs on the Java virtual machine. And it's in the OpenJDK. And a big thank you to our sponsors. We have JetBrains has donated a license of IntelliJ. We have Structure 101 has donated an IDE plugin license for their Structure 101 product. Hello Tomorrow has donated a one-year license to SonarGraph, and Venkat Subramaniam has donated a one-year subscription to agilelearner.com, and Webucator has donated a free course to their training as well. So thank you to all of our sponsors for helping us all get better. And thank you to Improve for hosting a meeting space, for providing pizza. And quick disclaimer, I do work here, but it is consistently voted the best place to work. And also, if you if you're running a startup, or if you know somebody who's a startup, let them know about Code Launch. It's coming back to Houston. So keep an eye on, go to codelaunch.com, keep an eye on that website. We have the Code Launch, the competition is going to come back, I want to say late March. So it's, we take, I guess, with 7 or 8 different startups, and we help them improve their solution, give them 24 hours worth of free development of a team of like maybe 4 people. And same thing with a bunch of other consulting companies in the area. A lot of fun. And then a couple days later, presentation is done, and there's absolutely zero ask for equity. The goal here is to help startups get started up faster, and it's just a lot of fun. And so again, go to codelaunch.com if you're interested. Keep an eye on the space, and I know that in the past, in some situations, there's actually been a prize purse. So it's pretty slick, pretty neat. Without further ado, Garrett, take it away, please.
Yes, thanks, Jim. Yeah, first of all, thanks for having me. It's great to be here. And today I talk about CRaC. Yeah, not the drug, but still, I hope I get you hooked on CRaC. So it's Coordinated Restore Checkpoint on the Java virtual machine. And just to make sure that everybody knows what it is, if you have a laptop and you close the lid and then you reopen it, the computer will be in the same state as before, right? So then what it does is you close it, and then the operating system recognizes, oh, the lid was closed. I store everything on the disk, and then when I reopen it, I restore it back to memory. So this is Checkboard and Restore. So about me, a little bit hard to see, but I think on the screen is better.
Yeah, looks great.
My name is Garrett Grunwald. I'm working for Azure Systems as a developer advocate, and I'm also a JUG leader and Java champion and other stuff, not that important. And at Azure we do JVMs, and we also do FooJ, which is the place to be all about Java. So if you look for something, then go to fooj.io, and you will find information about everything Java there. Okay. The slides, you can grab them here if you need them, but you will see them anyway because it's recorded.
Yeah, yes, exactly.
All right, so Java is great, and we have a vibrant community which needs a little bit get back into life after the pandemic. At least that's my impression. We have hundreds of Java user groups, thousands of free open source software projects, but the biggest star of the whole ecosystem is the Java virtual machine. I think we can all agree on that. The question is, how does it work? Because usually, as a developer these days, people use it but they have no idea what it is or how it works in the internal things, right? And I will give you just a very tiny, easy overview on the parts that are interesting for the CRaC project. So if we have a Java file, which contains your source code, then it gets into the Java C compiler, and then from there we create a class file which is cross-platform and contains the bytecode. And if you have this class file, you have a JVM on whatever operating system, then you can run that code using the JVM. Then in the JVM, we have a so-called class loader, which is here just very simple, but in principle, it's not that simple in the JVM, but we're not talking about class loaders here. So the class loader loads the class file into JVM memory. And from the JVM memory, it then gets into the so-called execution engine. This is one part of the JVM, and you see already it contains not only one thing, but multiple things. And it's the interpreter, it's the C1 JIT compiler, formerly known as NaN compiler, and the C2 JIT compiler, formerly known as server compiler. And then there's also profiler and the garbage collector, but we only talk about the first three parts because that's good to know when we talk about startup time. So how it works is as follows. First of all, we have the code that is in the JVM memory, and it gets first of all in the interpreter, and then the interpreter takes it line by line and converts it into the instruction set of the CPU. And the JVM is watching that, profiling. In principle, it's method counting. So if a method is called very often, then the JVM recognizes that, and then it takes this hot code of the hot methods and pass it forward to the C1 JIT compiler. And the C1 JIT compiler is, like I said, the formerly known client compiler. And this one is just fast. It compiles fast. Doesn't do a lot of optimizations here, and the reason for that is if you're running Java on the client side, then let's say you have IntelliJ or NetBeans or Eclipse, which are all Java applications, then if you double click the icon on the desktop, you would like to start it up like this. You don't want to wait until the compiler does the best optimizations, because in this case, you really would like to start it up fast. That's the reason why it doesn't do a lot of optimizations, but really just compile code as fast as possible. And then again, this compiled code is again watched or let's say it's profiled by the JVM, and the JVM will still look at it and see how often is this hot code called, and then there's another threshold, and if this is reached, the JVM will take this part of the code and forward it to the C2 compiler, including the profile information. And then the C2 compiler, that is the formerly known server compiler, this takes then the code and further optimize the code. The compilation and optimization takes longer, but the code that is the result of this compilation is much faster and it's better optimized. And this whole thing is named tiered compilation because we have multiple compilers that work together here. And then in this multiple compilers and interpreter, we have different levels of execution. And I just put them here on the list, but I don't go into that into detail. In the preferred way, it's first the interpretation, then we have the level 3, which is C1 compiled code, including profile information, and then level 4, which is C2 compiled code. This is, if everything's easy, then this is the way it works. And that leads me to the execution cycle. And the execution cycle is in principle the same that I explained before. With a little bit more information here. We have first interpretation, which is slow. Then we have a profiling phase, and then it gets into C1 compile, again profiling, C2 compile, and then there's this other thing that we see here, and this is decompilation. And this is a performance hit that we would like to avoid that if possible. The question is, what is de-optimization? I talk about the code will be compiled and optimized. Okay, that's cool. Why should I de-optimize code? That's the question. So de-optimization, there's a little example here. If we have a code block, which is just an if-then clause, and we just check if the value is greater than 0, the result should be 3, and if it's equal or smaller than 0, then it should be 0, the result, right? So this is the code. And now we profile that code, and we figure out this part is most of the times the hot part. It means, let's say in more than 90% of our cases, the value was greater than 0. So that means the compiler says, instead of checking this every time, I just reduce the code to this. I say the result is always 3. That's it. It's much faster, right? So because we don't have to do the check here, it's still guarded in the JVM. So the JVM still has an eye on this value. But the compiled code is really much faster here because there's just always 3. That means if we pass in a value equals 5, that means it's greater than 0, result is 3, everything's fine. But in case we have a value, suddenly we have a value equals 0, then this is not true anymore, right? And then we have to de-optimize. And that means we throw the whole code that was optimized away, take this block, interpretation C1, C2, and compile the complete block again. That means we had fast code, suddenly something happens, we have to throw the code away and do again the whole cycle, right? So, and this is de-optimization. You can imagine that it takes some time. And this is the performance hit that happens, let's say, when the application is warmed up and suddenly you have something like this, then you will feel it. It's really something you can measure. Okay, that's all great, but it really takes some time. And I've tried to come up with a chart about Jvm Startup because what you often hear these days is the Jvm is slow, you can't use it in microservices because it's so slow, the Jvm startup time is so long. The problem is if you take a Jvm and you create one class and there's just one method in main and you say system of runtime hello world, compile that and run that, and then you know how fast the Jvm can start up. Jvm is fast. That's not the problem. Your code has to be loaded. This is the problem because if you have something like, let's say you have Spring Boot, you have lots of dependencies, lots of classes, all this stuff has to be loaded before the first time of response. And this is that what the whole thing makes slow. It's not the Jvm alone. So the Jvm has to load and initialize stuff and do some optimizations. And then it has to load all the classes, initialize all the resources, kick up some application logic, do some optimization, and then your application comes with the first response. And this whole thing, this is the what we say, it's a Jvm startup. And then there's another thing, which is Jvm Warm-Up. That means if you start your application and the first time it responds doesn't mean it's fully optimized yet. It's the first time you can talk to the application, right? But it also means if you work with your application for some time, it might happen that caches will be filled or lists or whatever. So it will get faster over time and better optimized. That means if you wait some time, you will see it will get even faster, but it takes longer. And this is Jvm Warm-Up. This is a different thing. And if you hear people talking about the Jvm startup is so slow, then the first thing you should do is ask them, okay, why? Why is it slow? Explain it to me. And then most of the times, yeah, it's slow, Java is slow. This is the answer. It's not really right. So you just have to keep in mind if people talk about a slow Jvm startup, it really depends on what you start up. That's the main thing. Okay, and then we have Jvm performance graph. And on that graph, you see 3 colors here. Hopefully, yeah, you can see it on the screen. We have a yellow phase here. This is the interpretation phase. And you see it's not really long. And then we have the green phase, which is the C1 compile and profile phase. And then it gets into C2, which is the C2 compiler. And then you see, then the performance gets better and better until it reaches a specific level, and then it levels out there. So this is then what we say the Jvm startup is. And then we see these gaps, these periodic gaps here on the right side. This is usually garbage collection process. That means if the Jvm has a garbage collector, and from time to time it has to clean up the heap and compact everything, and then it has to stop the Jvm, do that, and then continue, and that is these gaps in the performance that we see here. But here in the beginning, we see other gaps, right? This is, and this is the optimization. This is the code was already fast, and suddenly something happens in the code, and it has to throw the code away and do the interpretation C1, C2 compile again, and that is this huge hit that we see here. That means you would like to avoid this phase. Right? Your application the first response might be here, but you would like to go there to avoid all this stuff if possible, and that takes some time. That's the problem. And if we put this into microservice environment, that means we start up the service the first time and we have to cope with the startup time, second time startup time, third time startup time, so that it sucks. Not really great. Okay. It would be much better if we can do something like that. The first time we started up. Okay. Second time we start from here, full speed. Third time. That would be great. The question is, do we have any solutions for that? There's something that helps with starting up, which is class data sharing. I don't know if you heard about that.
No.
That's interesting because it's already in for some, I think, can be JDK 5.
Okay.
And it's per default enabled since JDK 12. So if you use 17, then
Yeah.
you use it without knowing it. And the idea is that you can have it on application level and dynamic. That's the two modes. And it dumps class representations into a file. That means you load classes from the class path and then compile them. And when it loads the stuff, instead of loading it from all the different places, it puts the representation in a specific file. And the next time you start it up, it just loads it from that file.
So you could put it like on a volume in a Kubernetes.
And this is on the JVM itself. There's a specific folder in the JVM where it will store the stuff. And it's
Okay.
also JVM related classes. So the JVM itself also needs stuff
Okay.
to start up.
Okay.
And this is all in that files. And they can be shared among different JVM starts. Right? So
Okay.
that makes it faster.
Yeah.
And you don't have to handle any optimizations or hotspot detection because this is only class loading. Yeah. This is before it even gets into this phase with interpretation and that kind of stuff. That means we only reduced here the loading time of classes. But if you adjust it in the right way, you can start up to 2 seconds faster, which is a lot. It really depends. If we talk about microservices, then 2 seconds startup time.
It can add up.
Yeah. So there's a guy, Balozin. Unfortunately, I have to put a QR code here, and I need to do that. He has a blog post about how to tune CDS and app CDS, and he also gives session about that, only about this topic, because it's really, there are a lot of things you can optimize and make it even faster. And he told me that you can get up to 1 to 2 seconds out of that. And he has demos that shows that you can really gain that amount of time, which is great. But it happens here at the class loading level. So and at that point over there, we have interpretation compilation. So it doesn't really help us with this ramp up that we saw, right? And then we have ahead of time compilation. Probably everybody heard about that in the meantime. We don't have to interpret bytecodes here. There's no analysis of hotspots, no runtime compilation of code. We can start at full speed straight away. So that AOT means we have a native image, like a native executable. And Jvm native image does that. Right? So that means problem solved, right? We just use that. But not so fast, because AOT is by definition static. That means the code is compiled before it is run. So we take the code and compile it, right? And the compiler has no idea how the code is really used, how it will actually run. There is a trick to help here, which is called profile-guided optimization. And in Jvm, it is available in the enterprise edition, not in the community edition.
Yeah, that's right.
And that means the Jvm comes with a JIT compiler and with the ability to create native images. And what you do is you run your application the first time using the JIT, and you do profile, and then you store that profile. And when you create the native image, you take the profile information and apply it to the native image. And that's in principle, the way to try to make it faster. Right? That's the idea. The point here is you can only make it faster for one snapshot. It's the run that you did for the profile. It means if you apply the workload, then it will be optimized for this workload. That's the thing. Can help if you have short-lived microservices. It could be a good idea to do that. Jvm has some other things, and we come to that in a second. So I tried to put that in the same graph. If you just use plain AOT compiled code, then you might reach up to 60–70% of the JIT speed. Because in this case, the compiler has no idea about the code. It just takes the code and compiles it. Right? And then it makes some optimizations, but it's really, it can't really assume what's going on. If you use PGO, then you can gain up to 90%. Sometimes you can reach 100, and it gets better and better. That's for sure. But still, the JIT it has the ability to adjust over time to your code and to the code behavior, which is the big difference here. That means this is everything is static compiled code. Compile it once and then it runs forever like this. Where the JIT is, like, let's say, always in motion. Right? If the behavior changes, the JIT can adjust to that and can decompile, recompile, optimize, and all that. And this is the advantage. But also comes with some disadvantages, of course. And you need to run a profile run here for the PGO. Okay, if we compare AOT and JIT, then the AOT can has limited use of method inlining, which is some mechanism to improve the code. Because it can only do that in the profiling run, where the JIT can do that all the time. So it can always do method inlining aggressively on the code base. Then we don't have runtime bytecode generation in AOT. Where the JIT, you can do that, of course. Reflection this is a little bit tricky in Jvm. You can do it, but it's not that easy as it is in the JIT. You need to use some configuration files.
Yeah, I've done that before. It's tough.
So this is the biggest problem that people report to me when it comes to Jvm, and I ask to use it in production. No, why not? Reflection.
Yeah,
It's tricky, and I mean the guys from Jvm, they know that they work on that. And what you can't use is speculative optimizations. This is something like the JIT compiler can watch the code and figure out, oh, it looks like this part of the code is optimized or is used very often, so I optimize the code in that way. And if they change it, can use it, optimize it in a different way. The AOT code can't do that. It's just compiled once, and then that's it. But the JIT can really adjust to code. It can make stuff like branch prediction, things like that. So this is the speculative optimization. And we figured out that this is the huge amount of the performance benefit of the JIT comes from this speculative optimization. So you can see that this is really a big benefit. The overall performance of the AOT compiled code is typically lower than with the JIT, but that also depends on the application. So that's not really, it's a rule of thumb. The biggest disadvantage that I see with the AOT native image is that you develop in Java and then you compile it into native. It's in principle very similar if you remember GWT. You do something in Java and then it spits out JavaScript. That at least you could debug, but this is hard to debug because I had people that came to me and said, we have the problem that we wrote our stuff in Java, in IntelliJ, let's say. Then we do all the tests in the CI/CD system, everything's green. We compile a native image, we started and it fails. And they have no idea why, because all tests are green. The tests are running on Java code.
That they're working on allowing for unit tests to run in like native mode.
I don't know if you could, I bet you can do that somehow.
Yeah, and that's definitely something that my understanding is that they're working on that.
Yeah, because it's really tricky. Native code is different than JIT compiled code.
Yeah.
Definitely. Sometimes it's even completely different. So if you tap into this things, then yeah, you have really a problem because debugging is then really hard.
Debugging by logging.
Yeah, exactly. Yeah, you have to put something in, compile, run, check the log, and
and then sit there and wait while it recompiles the native.
Yes, it's really, this is what I see is for me the biggest drawback here. If it runs, it's great. If it doesn't run, okay.
Yeah.
Might be tricky. So on the other side, the AOT compiled code, very fast startup, where the JIT takes some time, as we saw. We have no overhead in the AOT, because if you have the JIT compiler, then I showed you its interpretation C1, C2, and at the same time, your code is already running. It means your application might even run already in interpreted mode. At the same time, it has to be compiled in the background. That needs more CPU power, more memory, which is definitely a disadvantage, right? And then for this reason also we have a larger memory footprint, because in the AOT compiled code, what happens here is the AOT compiler, native image compiler, it takes only the code that is really used, that is touched, and creates the native image. Where if you have the JIT compiler and you load, let's say, the library, but you only use one class of the library, the whole library will be there with all the classes. So that means it's much more memory that is used then. Okay, that means the main disadvantages of the JIT. It requires more time to start up. We have a CPU overhead to compile code at runtime, and we have a larger memory footprint. So these are the disadvantages. Okay. Let's take a look at a different approach. There's a project called Creo, checkpoint restore and user space. Really hard to read on this one here. So I have to look on my monitor. It's a Linux project. It's part of the kernel since 2013 already. So that means it's older. It's not really a new project. It's made to freeze running containers or application and then store the state of this application to disk, and later on restore from this data back into memory. That's the idea of Creo. And Creo is not the only project on Linux. There are different ones that do the same, but Creo is the, let's say, the most bulletproof version of that, and it works quite well. And that's also the reason why it's integrated already in OpenBC. Linux container, Docker, and Podman, they use all Creo in the background. Not always, but they can use it, let's say like this.
Huh.
So it's mainly implemented in user space, not in kernel. And the main goal was the migration of containers for microservices. It relies on the proc file system. And that also means if you have a Linux distribution that doesn't use proc, then Creo won't probably not work.
So not like Kubernetes, I'm guessing, since it.
As long as you have, let's say, I don't know which one, but it's usually all the Debian derivatives, they all use proc. So
Okay,
usually it's not a problem, but I saw that there are some Linux distributions that don't use proc. For example, on Mac, the Darwin stuff, it doesn't use.
yeah, okay.
So, and that's also one of the drawbacks, because Creo is not available on Windows and also not on Mac. It only works on Linux. Just keep that in mind. I will come to that later on.
Yeah.
And it can checkpoint a lot of stuff. So process and threads, application memory, memory map files, open files, files, firewalls, sockets. It's really a lot. So inter-process communication channels, timers and signals, and it can rebuild a TCP connection from one side only. So that's, which is interesting.
Yeah,
Usually you have to do this handshaking, but with Creo you don't have to.
wild.
Okay. Of course, it comes with some challenges too. Because if you would like to restart, so we have an application, we checkpoint the state to the disk, we take the files, put it on another machine and say, okay, restore. That's tricky, right? So because if you have another machine, that means, first of all, the architecture should be the same. You can't run an Intel stuff on an ARM architecture, won't work. Even if it's Linux, this won't work. If you have open files on that machine, and on the other machine, these files are not there, then this will also not work. And also shared memory and stuff. This is, it's hard. If you have everything on the other machine, then yeah, it will work, but this is tricky. Also, you can't really start it multiple times on the same machine, because on Linux you have a process ID, which is unique. And if it's taken, then you can't restart it one more time, it doesn't work. And yes, it also means if the PIT is already taken, and you would like to restore it, it doesn't work. Which could be tricky, but usually this is not a big problem. Not for the use case it was made for. And we also work on an idea where how you can fix that, because there are ways to do that. And the biggest thing is the virtual machine is an application that runs on Linux. So you should think, oh, I can just checkpoint it and restore it. It should work, right? And yes, the JVM itself might work. The problem is not the JVM. The biggest problem is your application. Because if you checkpoint the JVM and in the JVM you run your application, then the JVM is just the app will be just checkpointed to this, but your application is the thing that uses open files and has a database connection and stuff like that. The application has no idea what's happening, and when it gets restored, then the JVM might even start up, and as soon as your application starts running, then wait a minute, where's my file? Where's the database?
Yeah.
Yeah, and refresh.
I remember the support team one, company I worked for a few years ago. They would get virtual machine snapshots from customers, usually in the middle, and they would take these snapshots in the middle of a data processing run,
Oh.
basically.
Yeah.
They start up and then the application panics, you know?
Exactly, yeah, that's exactly the problem that you have.
Yeah.
So, and that leads me to CRaC. Because the most important part here is the coordinated restore and checkpoint. And the coordinated means that we find, or we implement a way to let the application know that now there's a checkpoint and now you got restore. So this is the important part, right? The JVM itself, this is possible to checkpoint, but the application inside the JVM, that was the tricky part. And what we do is we have a specific version of Creo and we bundle that with the JDK to make sure that it's really the same everywhere, because Creo comes with Linux. So that means there are different versions. It's also on your machine, but we need this specific version to make sure that it really works. And what we do is the heap is cleaned and compacted. It's in principle the same as with the garbage collection. We make sure that the heap is compacted and clean and the JVM is in a safe state. And then CRaC also throws checkpoint exceptions. So that means if you just run it and you forget to close something, then you will get an exception, which is a checkpoint exception. We tell you here in this class, that line of code, there's an exception. You have to do something.
Okay, interesting.
But I will come to that in a minute. So to make that possible, we have a simple API that makes it possible to react on checkpointing and restore. That's the main. And you can use either code. We have a command that from code you can create the checkpoint, or you can use JCommand to do
So that's from Java code.
from Java code. In the
Okay.
application, you can create a checkpoint.
Okay.
And at the moment, it's like this, that once you create a checkpoint, it will shut down the JVM.
Oh, wow.
That's what it is right now. But we have a solution since today that makes it possible to keep the JVM running. So it means you can create checkpoints in the background. And we use the save point mechanism, which is the same as the garbage collection, because people are sometimes wondering, okay, but I have multi-threaded code, so how can you make sure that everything's stopped correctly? But we don't have to, the JVM can do that anyway.
Oh, wow.
Garbage collection run does exactly this, right? You don't have to care about, oh, there's a garbage collection, I have to stop my threads. No, the JVM can do that and restart it in the running order.
Nice.
And we use just the same mechanism to do that. All right, so it is an OpenJDK project, so that doesn't mean, it's led by one of our engineers, by Anton Kossow, and he came up with this idea and how to implement it and all that. But it's not in our JVM. So this is an Oracle OpenJDK. It's an OpenJDK version where which is publicly available on OpenJDK.org project CRaC. And we provide the code there and hope that Oracle will accept it and put it into the official OpenJDK, but we can't guarantee. That's one of the reasons why I'm traveling around and tell it to everyone, that people try it and see the benefit. And yes, it is not cross-platform, it's only on Linux. But we even provide a library that you can use, and that makes it possible, let's say on Windows, this library will just it creates some kind of like a shade, like shadow library around the official API, and it will figure out if the JVM supports CRaC. If it does, it will use CRaC. If it doesn't, it will provide you with some dummy interfaces. So your code won't break in the IDE. If you run it, nothing will happen. But as soon as you have CRaC, then it will work. So that means you can develop on Windows and Mac, and then you can deploy to Linux, and then you can use it.
So what about Windows subsystem for Linux? Would it work on the WSL implementations that are available, that are, like, say, W-based on WSL? Would it work? Would CRaC work there?
Yeah, I think so.
Okay.
And in principle, you have just to check if it has the proc file system and if Creo is available. Usually it is.
Okay.
Because it's really a quite old project, so it's not that new. And I was also wondering, because it's all over the place, so really a lot of projects use that. Everybody knows it's a quite interesting project. And you can use it even on the command line. You can checkpoint an application by command line Creo, and then type in some parameters, and you can then create a checkpoint and stop an application. So it's a nice tool.
Yeah, sounds like it.
Yeah, if you find that on your somewhere on your disk, then you know it will work.
Okay,
So, and it's really called Creo. That's also the command is the same.
okay,
So what I told you is we have this coordinated. That means if you have a running application, and then at one point we create a checkboard from the outside, let's say we use J command, then we have to let the application know, here we create a checkboard, do something. The do something, I will explain that in a minute. And then we wait, and then when we store this running application, we again have to let the application know, now you get restored. Do something, right? That's the idea behind it. The restrictions, because we have to do that, because if you have open files or sockets, then, like I said, if you restore and the stuff is not available, then the application will crash. So that's the reason why we need these 2 points to let the application know. And to, that's really hard to read. So we have 2 commands, command lines parameters here, which is -x column CRaC checkpoint 2, and then equals path. And the path is just a folder. We just pass that to the Jvm. And in case a checkpoint will be created, the Jvm knows, in this path, I should store the checkpoint. That's the main idea. And then to restore it, we have -x column CRaC restore from, and then we point to the same path. And then the Jvm knows, oh, there is a checkpoint, I restore from there. That's the idea. Okay, then that leads me to the CRaC API, which is pretty simple. It's just one interface, and it only has 2 methods, before checkpoint, after restore. That's all we need. And you have to implement it everywhere where you access resources. That sounds terrible, because it sounds like, oh God, I have to change all the code. No, not really. Because usually it's just where you have socket connections, or where you have open files, stuff like that, database connections, all these kinds of things. And usually you have some kind like a database manager. And then this is then the class where you have to implement the interface. And then in the before checkpoint method, you would close the database connection. And in the after restore, you would just establish the database connection. This is the first method that is called after the restore. And with this, you can make sure that it will be there again, right? And to make that possible, that these resources get callbacks from the Jvm. In case there's a checkpoint, we need to somehow register them somewhere in the Jvm. So the Jvm should know, okay, you have these resource interfaces, but where are they? Right? So you register them in a so-called context. And then if you do that, then the context will take care that all these resources will be notified in case there's a checkpoint or a restore. And you can get this context by, there's the core class, core.get global context will give you this context as a static method. It's only one for all things in the Jvm, because this context needs to know all the resources in your code. And then you do it like this, you implement the interface, you get the global context, and then you register your resource into this context, and then that's all you need to do. Pretty simple. You can usually do that in the constructor of the class. Right. So and then this, I told you already, the context will take care about it maintains the list of the resources. And then it makes sure that they will be called, these methods before checkpoint will be called in the reverse order you registered them. Let's say you have a database, right? This is your first resource in class A. And then you have in class B, you have another resource that uses the database. So that means the first thing you have to do, you register the database, make sure the connection is there. The second thing is the second resource in class B. When you create the checkboard, the first thing you close then is B, and then the database. So just the reverse order. And in case we do a restore, then we just make sure that they will be registered or will be called in the same order we register them. So that means you can define the order in which these resources will be closed and restored. Or let's say these methods will be called. Okay, this is the method to create a checkpoint by code. It's called .checkpoint restore, and since today this name makes sense, because until yesterday it didn't really make sense, because we could only create a checkpoint and not the restore. But now there will be a parameter in the next JDK version that we will build where you can keep the JVM running. But with this, at the moment, it will shut down. And you will see that because I have a little demo for that. Okay. Or you can create a checkpoint by using Jcommand. That's what I usually do because in code it's the question if you have it's multiple things. You have to change the code and you have to add core checkpoint restore. Once you add that to your code, means every time it reaches this thing, it will checkpoint and will shut down the JVM. That means you do that once. The thing that you can do, you can check the folder where you store the checkpoint. If it's empty, you should create a checkpoint. If it's not empty, then just don't do it. Something like that is possible, but doesn't really feel good. So the question is, does it make sense or not to use that in code? This is your decision. It's possible. I use usually the Jcommand because then you can trigger it from the outside of the running JVM. So that leads me to a very simple example. You have it on the screen next to it. It might be, well, it's okay to read. It's a scheduled thread that will be called every 5 seconds. And then this will run a loop. And in that loop, I create random numbers from 1 to 100,000. And then I check these numbers if the number is prime. And to make it more realistic, this method uses a cache. Do not calculate it every time. And then it checks is the result in the cache. If it's in the cache, returns, and then this is pretty fast, right? Because it's just memory. If it's not in the cache, then I have to calculate if it's a prime number. And that if it's a large number, then it takes some time to do that. Then I get the result, store it in the cache, and then I return that slow. So in principle, this whole idea is to show if you have this interpretation C1, C2, right? It takes some time and it gets faster and faster. This will be the same behavior with this application. Because the first time you run it will be slow because the cache is empty, everything has to be calculated, and then it will be faster and faster. To make it more realistic, the cache, and that's what you usually do. If you cache something, you usually have a timeout for the values. But because you don't want to have the values forever in your cache. If they are outdated, you will just write them out. And this cache will do the same. It will start after 50 seconds, and then it will every 10 seconds, it will check if there are values that are older than 10 seconds, and we'll just write them out. Because the thread runs every 5 seconds, the cache will at one point always be filled. With just a little bit, a few will be removed and then added again and so on. But this is what you usually see if you run an application. It will never be really at one speed. It will always do like this. Depends on the workload and all that. So that means the first one is pretty slow because the cache is empty. Everything has to be calculated. And then with each iteration, it will be faster and faster because the cache will be more filled. And so the speed will increase. I did some tests on another machine. And you see here, it's just level 1, the application performance, and then here the number of iterations. And you see it was, in the beginning, it was very slow, and then it got faster and faster. And after the 9th iteration, it started to level out at some specific value. And this is exactly what I mean. Here, the cache was totally filled, and then some values have been removed, and again, and so on. So we see this, which is, you can take it as some kind of the same behavior that we see when the Jbm starts up. Okay, so the demo, and yeah, I have to look on this because it's hard to read. This is 2 shell windows here. On the left side, I just start the Java file with this parameter -wx checkpoint 2, and then I give it the /CRaC files folder. It means in this folder, I would like to store the checkpoint, and then I call -CRaC for .jar. That's the idea. And then I run it, and then you see some system out printers here. This is the order how I registered the resources, and then the first run was 27 seconds. So that means really slow. Right, so because the cache was empty. And then every run it gets faster and faster. So okay, then we get into milliseconds. And at some point, I reach something like 17 milliseconds here, and then I decide, okay, now it's a good time to create a checkpoint because it's fast. On the second shell window, I call now Jcommand, and then I use the jar file here. You can also use the PID. it's the same. So usually you use the page. In this example, I use the jar file, and the command is jdk.checkboard. And once I call that, we'll see on the first shell, we know it will call this before checkpoint methods in the reverse order. Then I register them in the beginning. Then it will create a checkboard, and then the JVM will be killed in this case. So will be shut down. I'm back to the shell. And now this is then the Jvm Warm-Up here, because in principle I warmed up the cache, right? That's what I did. But in principle, you can compare that to Jbm Startup Time. So I wait more than 10 seconds. And now I do the restore. I would expect now that because the cache will forget the values when they are older than 10 seconds. First time I hit the cache, it should wipe out all the values in the cache. And then it would lead us to again to this point here, 27 seconds. But it doesn't. And the reason for that is that I patched that problem. So the problem with CRaC is, and it's easy to understand, you take the application and you run it. And if you have time-dependent data, like timeouts or session timeouts, and you store them in somewhere, and then the next day you restore, then of course everything's outdated. So what I did here, in this method before checkpoint, I just created a variable that stores the epoch milliseconds. And this variable will be part of the checkpoint. And when I restore, I just do the same. I use the current epoch milliseconds and calculate the delta from the stored one. And then I know exactly the time between the checkpoint and the restore. And I apply that time to each value in the cache, and then it's up to date. But this is the stuff you have to do. That means if you have time-dependent data, it can lead to strange effects because you won't see any benefit from CRaC. The question is, where do you have really time-dependent data when you would like to create a checkpoint? It might happen, but then maybe this microservice is not really worth being checkpointed if it stores something like this, like time-dependent data, because if you restore, it doesn't make sense. Okay, so you have to think about it, just to keep that in mind. So then from that moment on, it runs with the same speed, and you see it continues running. I stopped at the 11th iteration, and it continues with 12, 13, and so on, and the cache is filled. So that means, and now I could also restore again from here. I can stop, and when I restore, it will again restore from here, from that stored checkpoint. That's the idea. Okay, so this is again from the command line. You use either the jar file or the bit, and then jdk.checkpoint, or from code, sorry, you can use code.checkpoint restore to do the checkpoint thing. Okay. The question is when to create the checkpoint. That's tricky because sometimes the developers know, okay, usually if we run the application for an hour and apply some test workload, then it's good, it's fast. Sometimes it can be even days, so it depends on the application.
After your cache is warmed up.
Exactly, yeah, it's some microservices take milliseconds, others take hours to warm up. So it's really, you can't really tell it, so that usually you know. So what we can tell you is you can do something like you run your application with a typical workload, and you start it with this parameter, -x plus print compilation. And then when you do that, your screen will be flooded with log outputs from the compilation. Each compilation will be logged on the screen. Sounds terrible, and it is, but at one point you will see that the amount of compilations will decrease, so that there will be less and less compilations. And then that means for you, oh, it looks like most of the code is compiled now and optimized. That is a good point to create a checkpoint.
So the beginning, is there any way to tie into that information and that's the JVM, via API calls so that you
Not yet.
Okay.
We'll be working exactly on that.
Yeah.
It makes sense to have some kind of a metric.
Yeah, heuristic something. Yeah.
Ask the JVM it's now a good time to create. a
Yeah,
checkboard,
yeah,
and
exactly.
Yeah, so we are working on that.
Okay, I was gonna say, yes,
Because it makes sense.
yeah,
It's hard for developers to do that. And in production,
right,
you
yeah.
can't.
And the ops teams, they just wanna run their application.
Yeah,
They're not gonna
exactly.
care. It's okay, is it running? Yes,
Yeah.
okay, great, you know?
Exactly. So yeah, it's, let's say it's in the making, so we're
Okay,
just
good,
trying to
good.
figure out a good metric that works in all different cases, because the
Yeah.
problem with this approach is if you have code that will be often de-optimized, then this compilation will never stop.
Yeah, and are you going only for class loads,
Yeah.
or are you going for
Exactly, you can also
cascades
do
too?
that, yeah.
You know, so yeah,
It's, we have some ideas how you can do that, and then it will come, something will be
yeah,
coming in there, because it makes sense. But as long as you just would like to play around, then this is a good indication to see how long it takes, how long does your code need to be compiled, for example.
yeah. And then how would you hook into that too? Is there maybe an API that you could provide that, you know, you say, okay, here's my map, keep an eye on it for, you know, whenever
Yeah,
the things stop being put in, and, you know, what was this increment, you know, something
yeah,
like that, you
it's
know?
just, yeah, because it's really on JVM level, so we will
Yeah.
probably provide something that makes it available to the developer
Yeah.
to give you an idea how to, or when to create it.
Yeah, and just, you know, create a listener, have a listener API
Yeah,
that would,
something like
that would listen to a map and say, hey, watch this map when it quiesces,
Yeah,
then take a snapshot, you know.
for
it's like-
example, yeah.
That
Yeah.
would make a lot of sense too.
Also, you can think about different things that you can do. At the moment, there we have, like I said, we have some ideas what you can implement and make available for developers. But we also need that to, if you would like to monitor it, the CRaC itself, you would like to see, okay, what's the startup time? And
Yeah.
so we need to know that, then it plays all in the same way. So we will definitely do something like that. And typical use case is, of course, not to run it on bare metal, but you use a Docker container, and then in the Docker container, you create a checkpoint, then you store the state of this container, and then you just start from this checkpoint to the state in this container. And then you can deploy that multiple times. You can scale it out, and every container will start from this checkpoint. That also solves the problem with this multiple pits on one machine, because it's like it's a
Yeah.
closed environment, right?
Yeah, yeah,
And then compatibility is also something you have to keep in mind. I already told you that it's only x64 at the moment, only Linux and only x64. An ARM port is possible, but we don't build one yet. So, and the majority of the servers running on Linux x64, so that's not a problem. Then we have something that we call upgrade. That means if you have an architecture like a Core i7, and then you restore it on the Core i9, that will work. And the reason for that is that the JVM is really smart because it optimizes the code not only for an architecture like x64, but even for the processor.
wow,
So it knows, oh, this is a Core i7 generation 5. I use this optimization of the code. Oh, this is a Core i7 generation 9. Oh, I can do different stuff. And if it's a Core i9, then this is more capable of doing things, so I do different optimizations. But this one, it's backwards compatible. It will support this code.
oh, nice.
But downgrading doesn't work. So that means if you create something on a Core i9, you can't run it on a Core i7.
Okay,
Right? So this is stuff, and this is only because the JVM is so smart. Right, because it can do this really CPU-specific optimizations, and that leads to these problems. We also work on that, so there might be a way to make it possible, but at the moment it doesn't work.
yeah, so the other thing that comes to mind is like, you have developers who run on like, you know, the i7, i9 series, and then the servers are run on Xeons, you know, so.
Yeah, that's exactly the point. So you have to try it. So I really, because I did the same here on this machine, because it works even on a Mac.
Okay,
So that means, because I can run a Docker container on
Yeah.
Mac, and in the Docker container I can run Linux, and this Linux will use the same processor that the Mac uses.
Yeah.
So it will also work on Mac.
I guess the best place to do it is like in some kind of a, if you're running it on the cloud, have a snapshot environment basically where
Yeah.
it takes a snapshot, some, some kind of staging or development or
Yeah,
something where you're gonna generate that snapshot
Yeah.
and then have it ready for production, because
Exactly.
you wanna have that staging and
it's,
production
it's,
almost
this is
identical.
really the tricky thing, and I come to that exactly here. It's if you have, in the cloud environment, you have this node groups. And usually, at least in Azure, it's guaranteed that these node groups have the same CPU architecture. So that means if you have a node group and you have 10 nodes, then all these 10 nodes will have Core i7 generation 5, let's say. But if you put that into a Kubernetes cluster, then you can put different node groups in there.
Oh, no.
That means you can have a node group that runs on Core i9 and one on Core i7, one on Xeon.
Yeah,
That doesn't work,
right.
right? So you have to make sure that if you use these node groups in a Kubernetes cluster, then you should make sure that all the node groups have the same CPU architecture.
Or maybe target the lowest common denominator.
Yes, exactly, yeah. Like I said, if you use a Core i5, for example, then it will work to the Core. I think the actual one is Core i12 or something, or 10. So yeah, so it will work on this environments then. And I know for sure in Azure it is guaranteed, and I talked to some guys from AWS and they told me it should be guaranteed. They couldn't really tell me, but yeah, it would make sense if it would mix up the architecture. It's because you would also run into other problems with native applications.
Okay.
Okay. So this demo program that I showed you, you can get on my private GitHub account, and I just give it to you because if you download the JDK and you can just fork that, it will directly run, and then you can play around with the code and figure out how it works. It makes it easier. So we patched the JDK, and I created the demo, and everything works fine. This is cool. Of course, we did also some tests on real applications, right, on frameworks like Spring Boot, Micronaut, and Quarkus. And XML transform is another thing where we made some tests. And this, what you see is the time to first operation. And this is on plain OpenJDK. I mean, Spring Boot took around 3.9 seconds to start up. Micronaut was a second. Quarkus was a little bit faster, 8 milliseconds, and this XML transform took 4.3 seconds. So if we use that in CRaC, then this is in the chance. It reduced the startup time to 38 milliseconds instead of 3.9 seconds. And for Micronaut, it was 46 milliseconds and Quarkus 33. That means this is in the range of native image startup.
Yeah. Oh, yeah.
And the reason for that is, and it's pretty clear, I think
Faster.
it's interesting that you see here it's 4.3 seconds, but it brings it down to really the same times. The reason is this time is compilation and optimization and all that. This time is loading from disk. And once it's optimized, then it's just load the stuff back to memory.
Yeah.
That's the reason why it's very similar from the startup speed. And that makes it so powerful. You can really bring down those startup times to really native image speed. These demos are available. So you can also just download the demos there and try it. And in the meantime, we have official support in Micronaut is a plugin available for CRaC. Quarkus has something working with CRaC. In Helidon, there's an issue open for support of CRaC. For Spring Boot, we had to patch the Tomcat and then point Spring Boot to that Tomcat and say, this is the embedded web server you should use to make it work. And the XML transform was just because we had something to show the difference. And the summary is that CRaC is a way to pause and restore JVM-based application. It doesn't require the closed world, like the native image. So it means closed world means native image needs to know all the classes. If it doesn't know all the classes, it will compile your code in a native image, but it doesn't work. And with the JIT or with the JVM, you don't need that. You can even at runtime, you can load code, and it will further be optimized and compiled. And we have extremely fast startup time and full performance. We don't need to identify hotspot and compile methods and all these things because we did that already. This is already compiled and optimized code. We start from the high performance, or let's say from the best performance possible, and we start from that point. So all the stuff that we needed to do before, we don't have to. And it gives us a really improved throughput from start because everything's warmed up, right? So it really depends when you create the checkpoint, of course. It can also fix the stuff. You remember the chart where I had the Jvm Startup, application startup, and application warm-up? It depends where you create your checkpoint. If you do it after the warm-up, then you have everything at full speed, fully warmed up directly. And then it's an OpenJDK project, and it can save infrastructure costs. And we also already mentioned that if we hit on the y-axis have the CPU utilization, and this is time, then usually we see this peak in the beginning. This is the Jbm Startup Time, and this is mainly interpretation, compilation, and optimization and all that. And I saw companies that to reduce this startup time, they buy nodes with a lot of CPU cores, right? And this stuff is very expensive. If you do it like this, you create a checkpoint here, and you see that after the initial peak, the CPU utilization drops to a specific level. And that means you can reduce the number of cores, and that means it is cheaper, and it can reduce the cloud cost. And then we start from there. And then we don't have to, we eliminate the startup time and the CPU overhead, but we still have the memory footprint, which is larger than with Creo, for example.
It depends on what problem you're trying to solve.
Yeah, exactly. So this is not, it's not really Jvm native image versus CRaC. It's another possibility to solve.
Another tool.
Yeah, exactly. So it depends. Sometimes Jvm is great. Sometimes you need a JIT if you need all the stuff that Java can do.
If you need reflection.
For example, yeah, it's much easier than if you have to load code at runtime or stuff, then Jvm doesn't work in that case. All the stuff is available on GitHub/CRaC. Also the demos and the OpenJDK version is, you can download it from there. There's an OpenJDK wiki, but there's nothing really logged in there. It's just for to make it complete. And then now let me show you the stuff running, because that's really interesting.
Yeah.
This one. So I have 3 share windows open here. And what I do is I first start, what I did, I showed you this demo that I wrote.
Can you share?
And
Do you share?
no, it's all good. So the first start that I do here, I start a Docker container, and I only start the jar file in that Docker container. And here it goes. And it takes some time. Like I said, 28 seconds for the first run, and then maybe 11 for the second. Because the cache is not filled. And if this is your application, and you need to wait until the cache is filled up, then that sucks. Because you wait 30 seconds. Come on. Still not there yet. First response. Yay. After 28 seconds. Second one to be faster because the cache is not filled. And then we will see, because it calls every 5 seconds, but it's so busy. Now we see all the threads are coming. Here we go. And then it will run every 5 seconds as expected, and still improving. Cache is still, there might be, now there's, at one point is even a hit from the cache will remove some stuff. I don't know where this is. Oh, let's see. But you see now it's, I would say now it's warmed up. Now it's fast enough, okay? So I shut it down. This is the typical Java, let's say Jvm Warm-Up. The next thing that I do is I created a checkpoint in that container, and now I restore from that checkpoint. And I did the checkpoint at the 17th iteration, so it will start from 18. Okay, and go. And here we go. And it's running. So it's fast, and we start from 18, and it's just running with full performance. And the good thing is, because in Docker, I can also start it on another window again, same container. And that's the big advantage, right? So you see that it was more or less instantaneously. And if I stop it here and restore again, there you go, right? So it's around 20 milliseconds for the run. And this is already the run. So that means this is 100,000 random numbers checked. So that means if I start it up like this for the first time, I don't have to wait until my application is warmed up. I can directly run with the warm-up thing. The cache is fully filled. And you can imagine that if you run that with a microservice, then it's really, that's awesome.
Yeah, oh, yeah. Last client I was on, we were using Spring Boot with Kafka, and it would take 30 seconds for the application to start up.
Yeah, exactly.
I did some experimenting with Jvm and it started up lightning fast, but it took a lot of work to get the file put together,
Yeah, it's a little bit tricky to do that.
Yeah, it was tricky. It was worth it, it's because the manager's like, okay, let's try it out and see how far we can get, It was an experiment, it's very, very kind of him, but I made it work, but it just never really saw the light of day, but it could certainly have saved some startup time.
The good thing with this is that it's just the JVM.
Yeah.
So you don't have to do anything. So you don't have to take care about, oh, do I use reflection here? Oh, have I all the files? And so it's really, you run it once and create a checkpoint. Then the next time you start it, it starts from there.
Nice.
Fully performance and just load it back into memory. Of course, if you have a lot of resources that you have to reopen, like files and stuff, then you have to do that, right?
Yeah.
But even that really doesn't take seconds. This is all milliseconds, right? So even if you create sockets, it takes a couple of milliseconds to re-establish the connection.
Yeah.
So that means the good thing here is you stay in the JVM, and for the JVM itself, it doesn't really know that it was stopped. So you restore it, and then the JVM says, hey, I'm here, I'm running for years, because it doesn't know, right? And that is, that's really powerful. So you can think about different scenarios. A little bit tricky at the moment is I'm just starting to play around with that is CI/CD systems, because you can think of usually you develop something and then you push it to the repository, and then it will get into the CI/CD system, the build pipeline, and then you will push it to staging. So the problem is you have to build the stuff, deploy it into a container, run the container, create the checkpoint, set the state of the container, and then deploy this container with the checkpoint. And the checkpoint has to be in the container. And it's a little bit tricky. At the moment, somehow I
you have to make sure you have good unit tests that are going to exercise all the code well enough.
I got to the point where I can build it. I use GitHub Actions to do that. And I build it, and I create the Docker container, and I run the application in the container. When I create the checkpoint, it somehow fails, and it's the same stuff that I do here. It works when I do it manually, but in GitHub Actions, for whatever reason, it throws the interrupted exception, and that avoids or prevents the checkpoint to run. And at the moment, we have no idea why it throws the exception, because it works on if you just do it on a Linux machine. But in GitHub,
is there stack traces generated?
Nothing really. It just shows that there is an interrupted exception. I don't know where it's coming from. It comes from the threadful executor, but it's not known on Linux usually. But in the GitHub Actions, it is. So I tried to catch that, but it didn't work. So I'm looking into that, because I would like to show people that you can do that in the CI/CD pipeline, right? Because this is interesting.
Yeah.
You don't want to do that manually.
No.
I mean, you can, in principle, because the thing is the following. This is nothing that prevents the code from running. All your tests will work.
Oh, yeah.
This is really just, in principle, it's the last step before you go to production.
Yeah.
And usually you don't have to do that for each build, because it's why? There's no benefit, because it's just to make it work.
Yeah.
And you don't deploy every build to production usually. So that means.
Or you have a pipeline where it does something.
So you might want to have something like a production pipeline, where you then, when you know everything's working, it's fine. Now we deploy to production, then you create the checkpoint shortly before that, and then deploy it. So that would be the idea, because it's not really needed to do that on every build. That would be too much. Yeah, so that's in principle it. If there are questions, then I mean it needs some time to get ideas to work around that, because it's really it's quite powerful. So you can do a lot of stuff and you can think about a lot of things, right? So you can even think about taking the state from one machine and run it on another machine. If it's the same machine, it will work. Or if it is in a Docker container. What I didn't try here is it should even run on Windows, because if it's on an x64 machine and you have Docker on Windows, I never touch it because I don't have a Windows machine. But if you have a Windows machine, can you run a Linux Docker container on that?
If you have
A Windows
machine, yeah, oh, yeah.
Then it will also
Yeah,
work on
yeah.
Windows, because I was not sure if it works, but it worked
Yeah.
directly on Mac, so I'm pretty sure it will work on Windows.
I've been able to run, Kafka container.
Yeah,
Kafka,
then you can run that even on Windows.
Yeah.
Which is nice.
Yeah.
I mean, that's the good thing, the beauty of the container stuff.
Mhm.
You can
Yeah.
really run it on different platforms.
Yep.
As long as the architecture is the same. So because like I said, I can't run that on my M1 Mac.
Yeah.
This
no,
is my
yeah,
old
yeah.
Mac. I just, and I hated that I have to take it with me because I have my new M1 sitting at home and I
Yeah.
can't use it
Yeah.
because I'm only on this x64
Yeah.
machine.
Oh, no.
But yeah, and it's fascinating. I mean, this is a 8-core, 32 gigabyte machine, with it should be fast, right?
Yeah.
The M1s are so fast.
Wow,
It's
wow.
really blazingly fast.
Yeah,
It's impressive.
yeah, I'd say, maybe reach out to
Oh, do you have, is that a Windows machine?
it is a Windows machine, yeah.
Do you have Docker on there?
I do.
Because I had the image on Docker Hub, you can just
Okay, yeah.
put it at startup.
Sure, yeah,
That
yeah.
would be great to see.
Yeah, sure.
It's, if you go to Docker Hub and then, I think Han Solo was more.
Yeah, sure, just a second here. Let me go ahead and share my screen. And,
Oh, yeah, I can stop sharing.
yeah, sure, I can share. It'll
You
take
can
a
stop it
few,
from
yeah,
there?
yeah. So
It would be
let's do that.
interesting
Yeah,
to
so
see.
let's try it out. Okay, so let's see here. Yeah, I just got started. So yes, let's see, what is,
Is it hub.docker or something like that?
yeah. Okay,
And then I think my username is Han Solo. Just look for Han Solo and then,
Han Solo. Yeah, it's got Han Solo, yeah, so.
yeah. And that should have,
Han Solo-san.
just Han Solo, yes, exactly, that's the one. And there's Han Solo / CRaC 4. That should have different.
Okay. It's a little cracked for, okay.
And then there is, just check the tags.
Okay,
And there is a tag. What is this time for machine?
it's I7.
Ah, perfect. Then there's a checkpoint. Here, this one, checkpoint I7.
Okay,
If
great,
you pull that one,
okay.
and then I give you the command to start it.
Sure, yeah.
This is cool.
Yeah, this is great.
Because I don't have a Windows machine, so I was not sure. I thought it should run, but I'm not sure if it really does. Oh, okay.
Docker pull. Also crack for checkpoint I7. Right, here we go.
Okay, so. And this is now okay, this is the bullet.
Yeah,
I will give you the command. That is cool.
yeah. Fun times.
It should be around 20 milliseconds startup time, I hope so.
Very, very fun.
Oh, that's cool.
Yeah.
Yeah, I had problems with Docker in the beginning to get it running in the Docker container. And the reason is that Docker also uses Creo.
Okay,
And then the Linux in Docker uses Creo, and then our JDK version comes with Creo. So, and there was a problem with that, but now this works, so that's great. Because before that, I only had I ran it on bare metal, just the jar file. And therefore I needed a virtual machine with parallels and all that, so I don't need that anymore.
all right.
Or, I can send you the command via chat, right?
Yes, you sure can.
Perfect.
Yeah.
Second. That's the chat. Oh, this is your, wait, I have to,
Yeah.
where's my chat?
Sorry, yes.
It's a little bit confusing, man.
Yeah, no, let me minimize this for your sake.
Okay.
Yeah, sorry.
No, good. Here. Okay. This is the command.
Yeah.
And now I'm really keen on seeing how that
Okay.
works. That would be cool.
Yeah. All right. Here we go. Unable to find Java latest.
What names? What name? Oh, sorry. Checkpoint underscore minus. Checkpoint underscore I7.
Ah,
Yeah,
there we go.
it's
Okay, all right.
Latest.
Docker, maybe?
Oh, no, sorry. The string one, you have to get, that's the name. Just name it CRaC one or something. It doesn't matter.
Like that?
Yeah.
Okay.
Yeah.
All right.
Ha!
Hey, all right.
That's so cool. So good.
Great, well, cool. So yes, it works on Windows, everybody.
Yes, that's proven now. Good. Oh, that's really good.
Fun times.
Yeah,
Great.
it's really good. Yeah, you see, it can really, you can deploy it on different systems,
Yes.
even on Windows.
Good
That's
stuff.
really cool.
Fun. Great.
Yeah, so, and in the repository on my GitHub repository, where I have the CRaC 4, there's also, I explain how to create a container so that you can do it on your own if you like.
Okay, nice, nice.
Because sometimes people just have no idea how to do that. You need 2 shell windows and then first of all, start a Docker container. In the Docker container, you start the application and then you log from a second shell into the same container and create a checkpoint.
Okay,
And
yeah.
then you have to let it run and then save the state of that container.
Yeah, that's
the
a bit
different
tricky.
image. That's a little bit, it's, yeah, but it's the only way I was able to really do it
Yeah.
easily.
Yeah. Makes sense.
And it's, I described that in the README of the CRaC.
Yeah, you could maybe put together like shell scripts instead of having to,
Yeah,
maybe.
yeah, I'm not sure because the problem is that, and this is my problem with GitHub Actions at the moment, I have no idea how to manage, because I have just one pipeline in GitHub Actions, right? So if I start it up, then I can start the Docker container and start the application in the Docker container. And now I somehow have at the same time log into that container to create the checkpoint. I can also do that by code. That's what I tried. But the
Right.
problem there is if you do that, if you start up the container and directly run the code, when you stop the code, it will shut down the container. So you need to get the container running, be able to state the
Yeah,
state of
yeah.
the container. So that is the tricky part. I have to figure out how to do that. I have some ideas, but at the moment I can't really check one that it throws this exception there.
Yeah, have you reached out to the GitHub Actions team?
No, not yet, because
Okay.
I think the problem might be related to how we do it, but
Okay.
I'm not sure yet. So it's interesting that we only see that exception in the GitHub Actions and not on the normal Linux machine. You don't see it. So, but once I get that running, that's really cool because then I can really build it. And it would be nice to demonstrate from the IDE. I change something and then I just do a run in GitHub Actions and then I pull it from Docker Hub and then run it and see the
Nice.
change. That would be great.
Very cool.
Yeah, so that's CRaC.
All right, great. Thank you. This has been great.
Thank you.
Yeah.
Awesome
Hopefully
talk.
it'll be
Good to
interesting.
talk to you again.
Oh, we have visitors here.
Yes, that's great, yeah.
Yes, it's a good stuff. It's a good project. So could be really interesting for people that have problems with startup times. And even like you said, if you run Kafka and you don't need high performance, but you suffer from long startup.
Yeah.
This could also solve that one.
Absolutely.
I mean, you have to keep in mind that if you run a JVM with a large heap, then the files will be larger, right?
Yeah, I'm gonna say, yeah, because kind of it's a memory snapshot.
Yeah.
It's like
So-
if you do a heap dump and out of memory exception, and you're
Exactly.
running on a 4 gigabyte, or they say a 32 gigabyte heap, on a
Yeah.
large system,
I mean, it will be compacted and cleaned, but still, I mean, if there's so much in the heap, then it will
Yeah.
be stored.
yeah,
And this demo that I showed you has 31 megabytes that's the file size. So in principle, it's one large file and it's the whole heap and all that. And then you have a couple of, I think it's around 30 files, and the rest is just tiny files then.
Okay.
And this is the whole snapshot.
Okay.
There's another thing. Oh, wait, what was it? Oh, yes, because the question came up, oh, is that stuff encrypted? It's not.
Okay.
But it's binary code, so it's not really something that you can read. So it's because Creo does that on an operating system level. So it takes really the compiled code from memory and dumps it into the file. So it's not really something you can just easily debug or something.
Yeah, no.
And because it's usually part of your container, it's not accessible somehow easily.
Okay.
Shouldn't be a problem. And one other thing which is interesting is that Creo, because it does that on the operating system level, it uses the PID in Linux. And everything that is related to the PID will be checkpointed. That means if the JVM uses off-heap memory, even that will be checkpointed.
Okay.
And that is cool because you can't do that with other stuff.
Right.
But because this is related to the PID, Creo will, oh, this belongs to that, check.
Oh, so it will grab the off-heap memory.
The off-heap memory,
CRaC will grab that?
Yeah, and it will
Wow.
store it in the checkpoint and it
Okay.
will restore it again.
Wow, nice.
So which is really cool. Because
Yeah.
if you use off-heap memory, I mean, it's not really that often that people use that, but if you use it,
Yeah.
then CRaC will checkpoint it.
Yeah,
Yeah.
because that, like, with HTTP, have like heaped up out of
Yeah.
memory exception, it wouldn't grab that,
Yeah,
so
exactly.
you have no clue what's going on.
But this will grab it because,
Wow.
and this is because it's related to the PID. Everything that belongs to this PID, doesn't matter what it is, will be taken from Creo and will check.
That's like, it's great.
And that's really cool. It's a cool, that makes it really useful.
Yeah, oh, yeah, absolutely.
Let me think about if there's something more. I don't think so. I think this is all I know about CRaC. Oh, it's already 8:30.
Yeah, that's great. No, that's good. This has been fantastic. Thank you so much, Garrett. And thank you everybody for joining from online. And thank you if you stuck around this long on YouTube. Thanks for sticking with us. And we'll see you next time. Thanks so
Yes.
much. Take care.
Thanks
Bye.
again.
All right. Stop recording here and there we go.